This meeting is being recorded.
In section 7.6, we're going to review this concept of alkene stability. And this will lead us on our way to be able to predict products of these types of reactions, specifically elimination reactions to produce alkenes, if we have a general understanding of the stability of our different products that could be produced. So in this first line here, we're going to look at steric strain specifically with the two possible isomers of butene. So we know that we have 4 carbons and a double bond somewhere in this compound. So we see this trans 2 butene over here, where the two methyl groups surrounding these two positions here, the two vinyl positions, are far apart from one another. Whereas with the cis orientation of 2-butene, we have what's indicated here as steric strain. So these two methyl groups are closer to one another, and this generally is less stable because it would be higher energy to produce this conformation of the compound. So this isomer again, is generally going to be less stable because of that steric strain. And we can see this in evidence here through our process of heat of combustion comparison. So what we have down here is the trans isomer up top, the cis isomer below, and we see that there's actually more energy release, so a higher magnitude here, this 2686 over 2682, in this enthalpy change overall. So we know that the cis isomer must have been at a higher energy, so this reveals the relative stability of these two isomers. So you may be wondering, how will this help you predict products? So generally, the more stable, the lower energy representation of an alkene would be our major product. So that's what we see here. This representation of the heat of combustion shown. We have the same product, so we know that we are at the same energy at the end point here, but our cis isomer would have to start 4 kilojoules per mole higher than our trans isomer to produce these changes in enthalpy. So there is another way to rank alkene stability besides cis versus trans comparisons. We can also look at whether or not our alkene is monosubstituted. So here's our double bond here. We have 3 hydrogens, so only one position has a substituent, so monosubstituted. We see di-substituted here if we fill in the hydrogens, tri-substituted, and then our most stable compound would be a tetra-substituted alkene, which would have 4 alkyl groups, which are highlighted here. And the reasoning behind this is something that we call hyperconjugation, and you'll just need to know a very brief definition that the increase in alkyl groups help to stabilize the CC pi bond via this term that we use called hyperconjugation. So in the end, the simple way to look at this, the more alkyl groups, the more stable the alkene. So when we talk about cyclic alkenes, so cycloalkene stability, whenever we have a cyclic alkene with less than 7 carbons, only the cis alkenes are stable. And it would require too much energy to keep a trans conformation possible. Some of these rings definitely could not even exist, like the cyclopropene here with a trans bond. And there's a specific rule that we say, Brett's rule here, when we talk about bridged bicycloalkenes. So this specific rule, again, applies to bicyclic compounds, cyclic alkenes. And if we have a bridgehead here, with a double bond, this compound is not very stable. if we have less than 8 carbons, we cannot have a bridgehead, definitely not with a trans pi bond here, right? Unless one of the rings has at least 8 carbons. Briefly, the geometry at the bridgehead will prevent this overlap of the p orbitals. So it would be strained and it wouldn't be able to keep that positioning. So again, the larger ring can be stable. So we'll continue with a discussion about elimination reactions next time.